U.S. Physics Olympiad Year 2024 F equal MA. This year, as usual, 75 minutes were given for 25 problems. If you want to stay up to date with interesting Olympiad problems, subscribe to this channel. I offer private tutoring for Physics Olympiad preparation. I currently have openings. There is a discount for group classes. Message me if interested. My email is fred1996@hotmail.com. Problem number 1. An archer fires an arrow from the ground so that it passes through two hoops, which are both a height h, above the ground. The arrow passes through the first hoop 1 second after the arrow is launched, and, through the second hoop another second later. What is the value of h? Solution for the problem number 1. Obviously the times t1 and t2 satisfy the equation gt square over 2 minus v0 t plus h equals 0, where v0 is the initial upward velocity. Therefore, we have equation 1, from which we read off equation 2. Plugging in the numbers gives h equal 10 meters. Alternatively, notice that if the arrow is at the same height at time t1 1 second and t2 equal 2 second, then it must have reached the top of its trajectory at time t equal 1.5 seconds. So it was launched with vertical velocity 15 meters per second, in the first second. The average vertical velocity is therefore 15 plus 5 over 2, which is equal 10 meters per second, giving h equal 10 meters. That was answer B, which is solution for the problem number 1. Problem number 2. An amusement park ride consists of a circular, horizontal room. A rider leans against its frictionless outer walls, which are angled back at 30 degrees with respect to the vertical, so that the rider's center of mass is 5.0 meters from the center of the room. When the room begins to spin about its center, at what angular velocity will the rider's feet first lift off the floor? Solution for the problem number 2. When the rider's feet just lift off, the normal force N from the floor vanishes, so the riders only experience a normal force from the walls. That normal force must both cancel the downward gravitational force mg, and provide the inward centripetal force m omega square r. So we have next two equations. Thus, tangent theta equals g over omega square r. Solving for omega and using tangent 30 degrees equal 1 over root 3 gives omega equals 1.86 radians per second. This is the answer A, and that was solution for problem number 2. Problem number 3. A simple bridge is made of 5 thin rods rigidly connected at 4 vertices. The ground is frictionless, so that it can only exert vertical normal forces at B and D. The weight of the bridge is negligible, but a person stands at its middle, exerting a downward force F at vertex C. In static equilibrium, each rod can be experiencing either tension or compression. Which of the following is true? Answer A. Only the vertical rod is in tension. Answer B. Only the horizontal rods are in tension. Answer C. Both the vertical rod and the diagonal rods are in tension. Answer D. Both the vertical rod and the horizontal rods are in tension. Answer E. All of the rods are in tension. Solution to problem number 3. Points A, B, C and D are in equilibrium. Points B and D are subject to the reaction forces of the bridge support, which, due to symmetry, are equal to F in half. To balance the vertical component on points B and D, force T1 must be a compression force and is equal to F divided by the square root of 2. Further, to balance the vertical component on point A, force T2 must be a tension force and is equal to F. And to balance the horizontal component on points B and D, force T3 must also be a compression force and is equal to F in half. Thus, the forces in the vertical and horizontal rods are tension forces, and in the inclined ones, compression forces. This is answer D, and this is the solution to problem number 3. Problem number 4. A bouncy ball is thrown vertically upward from the ground. Air resistance is negligible, and the ball's collisions with the ground are perfectly elastic. Which of the following shows the kinetic energy of the ball as a function of time? Assume the collisions are too quick for their duration to be seen in the plot. Solution to problem number 4. When the ball is in the air, its velocity is vt equal v0 minus gt, so its kinetic energy is proportional to v squared, which is v0 minus gt squared. It is a concave up parabola. When the ball bounces, its speed stays the same, so the kinetic energy stays the same and there's no discontinuity. The graph of D corresponds to this behavior. That was solution to problem number 4. Problem number 5. A massless inclined plane with angle 30 degrees to the horizontal is fixed to a scale. A block of mass m is released from the top of the plane, which is frictionless. As the block slides down the plane, what is the reading on the scale? Solution to problem number 5. The scale reading is equal to the vertical component of the normal force of the block on the plane. The magnitude of the normal force is mg cosine theta, and the vertical component is cosine theta times this, so the reading is mg cosine square 30 degrees, which is 3/4 mg. This is answer C, and that was solution for problem 5. Problem number 6. A pendulum is made with a string and a bucket full of water. When the string is vertical, the bottom of the bucket is near the ground. Then, the pendulum is set swinging with a small amplitude, and a very small hole is opened at the bottom of the bucket, which leaks water at a constant rate. After a few full swings, which of the following best shows the amount of water that has landed on the ground as a function of position? Solution to problem number 6. The amount of water at each location is proportional to how long the bucket spends there, so it is inversely proportional to the velocity. Therefore, it is the lowest, but non-zero, at the middle, where the bucket has maximum velocity, and highest at the endpoints, where the bucket is turning around. This is answer C, and that was solution for problem 6. Problem number 7. A particle travels in a straight line. Its velocity as a function of time is shown below. Which of the following shows the velocity as a function of distance x from its initial position? Solution to problem number 7. The particle accelerates uniformly, then travels at a constant velocity for some time, then decelerates uniformly down to resting. As a function of distance, then, the velocity must also increase, then stay constant for some time, then decrease down to 0. Since velocity versus time is symmetric, velocity versus distance must be symmetric as well, which is case A, B or C. If the movie were played backwards, it should look the same. When the particle is accelerating uniformly, its velocity is proportional to t, while the distance is proportional to t squared, for example, as in free fall. Consequently, velocity is proportional to the square root of distance. This is answer C, and that was solution for problem 7. Problem number 8. A rod of length L is sliding down a frictionless wall. When the rod makes an angle of 45 degrees to the horizontal, the bottom of the rod has speed v. At this moment, what is the speed of the middle of the rod? Solution to problem number 8. The bottom of the rod has rightward velocity v, so by symmetry, the top of the rod has downward velocity v. The velocity of the middle of the rod is the average of these velocities, and thus has magnitude equal v over square root from 2. This is answer B, and that was solution for problem 8. Problem number 9. When a car's brakes are fully engaged, it takes 100 meters to stop on a dry road, which has coefficient of kinetic friction mu k equals 0.8 with the tires. Now suppose only the first 50 meters of the road is dry, and the rest is covered with ice, with mu k equals 0.2. What total distance does the car need to stop? Solution to problem number 9. When the road is dry, the work done on the car by friction is equal to mu d mgx, where mu d is the coefficient of friction with the dry road and x equals 100 meters is the braking distance. This work should be equal to the car's initial kinetic energy k. In the second case we use half of kinetic energy for the first 50 meters and other half for the ice road, which is giving equation 1. So from here we have distance on the ice road is 2x. And total distance d equal x over 2 plus 2x, which is 250 meters. This is answer C, and that was solution for problem 9. Problem number 10. A block of mass m is connected to the walls of a frictionless box by two massless springs with relaxed lengths L and 2L, and spring constants k and 2k respectively. The length of the box is 3L. The system rotates with a constant angular velocity omega about one of its walls. Suppose the block stays at a constant distance r from the axis of rotation, without touching either of the walls. What is the value of r? Solution to problem number 10. We balance forces on the block in the reference frame rotating with the box, to give equation 1, solving for r gives the answer D. That was solution for problem 10. Problem number 11. Two hemispherical shells can be pressed together to form an airtight sphere of radius 40 centimeters. Suppose the shells are pressed together at a high altitude, where the air pressure is half its value at sea level. The sphere is then returned to sea level, where the air pressure is 10 power 5 pascals. What force F, applied directly, outward to each hemisphere, is required to pull them apart? Solution to problem number 11. The inward pressure force on each hemisphere is pi r squared delta p, where r equals 40 centimeters and delta p equals 10 power 5 pascal. Plugging in the numbers gives a force of 25,000 newtons. That was the answer A. And that was solution for problem number 11. Problem number 12. A space probe with mass m at point P traverses through a cluster of 3 asteroids, at points A, B, and C. The masses and locations of the asteroids are shown below. What is the torque on the probe about point C? Solution to problem number 12. Only asteroids A and B contribute to the torque. Using the standard formula for torque, we have impression 1, that was answer A. And that was solution for problem number 12. Problem number 13. Two frictionless blocks of mass m are connected by a massless string which passes through a fixed massless pulley, which is a height h above the ground. Suppose the blocks are initially held with horizontal separation x, and the length of the string is chosen so that the right block hangs in the air as shown. If the blocks are released, the tension in the string immediately afterward will be T. Which of the following shows a plot of T versus x? Solution to problem number 13. This problem can be solved with limiting cases. When x equals 0, this reduces to an Atwood's machine, with equal masses. Both masses are static, so the tension T equals mg. When x going to infinity, the string becomes horizontal, so equating the accelerations of the two masses gives A equals g minus T over m, which equal T over m, which yields T equals mg over 2. The only choice satisfying these limits is B. Alternatively, with a little trigonometry, you can show that the tension could be found from next three equations. Solving for T giving us expression 4, note that in general, the tension also depends on the initial speeds of the blocks. In this problem, we have made the simplifying assumption that the initial speeds vanish, and answer B is solution for problem number 13. Problem number 14. A bead of mass m can slide frictionlessly on a vertical circular wire hoop of radius 20 cm. The hoop is attached to a stand of mass m, which can slide frictionlessly on the ground. Initially, the bead is at the bottom of the hoop, the stand is at rest, and the bead has velocity 2 meters per second to the right. At some point, the bead will stop moving with respect to the hoop. At that moment, through what angle along the hoop has the bead traveled? Solution to problem number 14. When the bead stops moving with respect to the hoop, they must have the same velocity. By conservation of horizontal momentum, that velocity must be half the initial velocity. Thus, by conservation of energy we have equation 1. Here delta H is the change in height of the bead. Solving gives delta H equals 10 centimeters, which implies the bead slides by 60 degrees along the hoop. This is the answer C, and that was solution for problem number 14. Problem number 15. The viscous force between two plates of area A, with relative speed v and separation d, is F equals eta AV over d, where eta is the viscosity. In fluid mechanics, the Ohn-Zorge number is a dimensionless number proportional to eta, which characterizes the importance of viscous forces in a drop of fluid of density ρ, surface tension, gamma, and length scale L. Which of the following could be the definition of the Ohn-Zorge number? Solution to problem number 15. From the definition of viscosity, the units of eta are kilogram meter per second. In addition, the units of ρ are kilogram per cubic meters and the units of L are meters. As for the surface tension, it is a force per length, so its units are kilograms per square seconds. So due to dimensional analysis we have to combine from these three units proper power equation of type 1. And find the corresponding power coefficients alpha, beta and gamma. Solution will be alpha equal beta equal gamma equal 1/2. We thus conclude that square root from ρ gamma L has the same units as eta, so that choice, E, is the only possibility proportional to eta, that is properly dimensionless. This is answer E, and that was solution for problem number 15. Problem number 16. A child of mass m holds onto the end of a massless rope of length L, which is attached to a pivot at height h above the ground. The child is released from rest when the rope is straight and horizontal. At some point, the child lets go of the rope, flies through the air, and lands on the ground a horizontal distance d from the pivot. On Earth, the maximum possible value of d is dE. If the setup is moved to the Moon, which has 1/6 the gravitational acceleration, what is the new maximum possible value of d? Solution to problem number 16. This problem is most easily solved using dimensional analysis. D must be some function of L, H, M, and G. Of these, G is the only value that contains seconds. Since D does not contain seconds, distance cannot depend on the value of G, thus, the correct answer is C. This is the solution to problem number 16. Problem number 17. Consider the following system of massless and frictionless pulleys, ropes, and springs. Initially, a block of mass m is attached to the end of a rope, and the system is in equilibrium. Next, the block is doubled in mass, and the system is allowed to come to equilibrium again. During the transition between these equilibria, how far does the end of the rope, where the block is suspended, move? Solution to problem number 17. When the block is doubled in mass, it increases the tension in the bottom string by mg, so the third spring's length increases by delta x3 equals to mg over 3k. Since the bottom pulley has two ropes pulling down on it, the downward force on it increases by 2 mg, which means the upward force on the top pulley also has to increase by 2 mg, so the tension in the top string also increases by mg. Then the first and second springs increases in length by delta x1 equals mg over k and delta x2 equals mg over 2k. Finally, by considering how changes in length of each spring affect the position of the mass, we conclude total delta x equals sum of all three enlargements, which is 11 mg over 6k. This is answer E, and this is the solution to problem number 17. Problem number 18. A satellite is initially in a circular orbit of radius r around a planet of mass m. It fires its rockets to instantaneously increase its speed by delta v, keeping the direction of its velocity the same, so that it enters an elliptical orbit whose maximum distance from the planet is 2r. What is the value of delta v? Hint: when the satellite is in an elliptical orbit with semi-major axis A, its total energy per unit mass is negative gm over 2a. Solution to problem number 18. The initial speed in the circular orbit is v initial equals square root from gm over r. In the elliptical orbit, the semi-major axis is a equals 3r over 2, so the total energy per satellite mass is negative gm over 3r equal negative gm over r plus 1/2 v final square, which implies v final square equal 4 over 3 mg over r. So from here we have v final minus v initial equal answer B. This is the solution to problem number 18. Problem number 19. A wheel of radius r has a thin rim and 4 spokes, each of which have uniform density. The entire rim has mass m, 3 of the spokes each have mass m, and the fourth spoke has mass 3m. The wheel is suspended on a horizontal frictionless axle passing through its center. If the wheel is slightly rotated from its equilibrium position, what is the angular frequency of small oscillations? Solution to problem number 19. This system is a physical pendulum. The moment of inertia about the center is in expression 1. When the system is rotated a small angle theta from equilibrium, the restoring torque comes from the difference in masses of the top and bottom spokes in expression 2. So we have equation number 3 for rotational motion. As a result, we have expression 4 from which we read off omega equals square root from g over 3r. Which is answer A. This was the solution to problem number 19. Problem number 20. 4 massless rigid rods are connected into a quadrilateral by 4 hinges. The hinges have mass m, and allow the rods to freely rotate. A spring of spring constant K is connected across each of the diagonals, so that the springs are at their relaxed length when the rods form a square. Assume the springs do not interfere with each other. If the square is slightly compressed along one of its diagonals, its shape will oscillate over time. What is the period of these oscillations? Solution to problem number 20. Suppose that one of the masses has moved by amplitude a from its original position, and it currently has speed 0. By symmetry, all of these masses have maximum speed v maximum in equilibrium position when displacement is 0. So, the total maximum kinetic energy of all four masses equal to total potential energy of springs, and we have equation 1. From this equation we have V maximum equals square root from 2k over m multiplied by amplitude a. But from other hand for the harmonic oscillation we have expression V maximum equal omega multiplied by amplitude, so finally omega equals square root from 2k over m and period t equal 2 pi multiplied by square root from m over 2k. That was answer B, and this was the solution to problem number 20. Problem number 21. A syringe is filled with water of density ρ and negligible viscosity. Its body is a cylinder of cross-sectional area A1, which gradually tapers into a needle with cross-sectional area A2 much less than A1. The syringe is held in place and its end is slowly pushed inward by a force F, so that it moves with constant speed V. Water shoots straight out of the needle's tip. What is the approximate value of F? Solution to problem number 21. If the water has speed v' when it leaves the needle tip, then A1v equal A2v'. The water outside the syringe has atmospheric pressure, so by Bernoulli's principle, the pressure P of the water inside the syringe obeys equation 1. The required force is the area times the pressure difference. That was answer D. Incidentally, if you don't know Bernoulli's principle, you can also solve the problem by equating the power, Fv with the rate of change of kinetic energy of the water. This was the solution to problem number 21. Problem number 22. A spherical shell is made from a thin sheet of material with a mass per area of sigma. Consider 2 points, P1 and P2, which are close to each other, but just inside and outside the sphere, respectively. If the accelerations due to gravity at these points are g1 and g2, respectively, what is the value of absolute value of g1 minus g2? Solution to problem number 22. Suppose the shell has radius r. By the shell theorem, the gravitational field vanishes inside, so g2 equals 0. The gravitational field just outside has magnitude g1 equals gm over r square, where mass m equals 4 pi sigma r square is the total mass of the shell. Thus, the unknown variable r cancels out, and the answer is 4 pi g sigma. That was answer D. Note that this is actually a universal statement. Above, we found that it didn't depend on the sphere's radius, but more generally, it is true regardless of the shell's shape. The reason is that g1 minus g2 is solely determined by the mass near P1 and P2, and if one zooms in enough to a patch of any surface, then it always looks like an infinite plane, so the answer doesn't depend on the shape of the surface away from that patch. This was the solution to problem number 22. Problem number 23. Collisions between ping-pong balls and paddles are not perfectly elastic. Suppose that if a player holds a paddle still and drops a ball on top of it from any height h, it will bounce back up to height h over 2. To keep the ball bouncing steadily, the player moves the paddle up and down, so that it is moving upward, with speed 1 meter per second whenever the ball hits it. What is the height to which the ball is bouncing? Solution to problem number 23. In the reference frame of the paddle, the ball loses half its energy during the collision, so the speed of the ball immediately after the collision is 1 over root 2 of its speed immediately before the collision. Let v be the speed of the ball relative to the ground immediately before the collision, then we have equation 1 to find speed of the ball right after the collision in our original frame of reference. From here v equals 5.83 meters per second. The height of the bouncing is v square over 2g, which is 1.7 meters. This is the answer D, and that was solution to problem number 23. Problem number 24. When a projectile falls through a fluid, it experiences a drag force proportional to the product of its cross-sectional area, the fluid density ρf, and the square of its speed. Suppose a sphere of density ρs much greater ρf, of radius r is dropped in the fluid from rest. When the projectile has reached half of its terminal velocity, which of the following is its displacement proportional to? Solution to problem number 24. During the fall into the liquid, gravity and braking force are applied to it, described by equations 1. Since the mass of the body is expressed by formula 2, and therefore acceleration is the derivative of velocity with respect to time, gets a simple differential equation with separable variables 3, through which the dependence of velocity on time is observed. Here the coefficient beta is expressed by formula 4. Next, since time is expressed through distance and velocity by formula 5, we can use it in formula 3 to display the dependence of distance on velocity through formula 6. This formula is easily integrated as 7. Next, using the expression for terminal velocity 8 and the expression for half terminal velocity 9, we get the final answer in the form of 10, which gives us the distance dependence on densities and radius in the form of an answer B. And this was the solution to problem number 24. Problem number 25. A yo-yo consists of two massive uniform discs of radius are connected by a thin axle. A thick string is wrapped many times around the axle, so that the end of the string is initially a distance r from the axle, then, the end of the string is held in place and the yo-yo is dropped from rest. Assume that energy losses are negligible, and that the string has negligible mass and always remains vertical. Below, we show a cross-section of the yo-yo partway through its descent, between the moment the yo-yo is released and the moment the string completely unwinds. Which of the following is true regarding the yo-yo's acceleration? Answer A. It is always 0. Answer B. It points downward, but decreases in magnitude over time. Answer C. It points downward and has constant magnitude. Answer D. It points downward, but increases in magnitude over time. Answer E. None of the above. Solution to problem number 25. As the string unwinds, the radius small r of the string remaining about the axle decreases. Specifically, if the yo-yo has fallen a distance c, and the string has total length l, then small r square over big R square equal l minus c over l. This change in R affects how the energy of the yo-yo is divided between translational and rotational motion. If the disks have total mass m, conservation of energy gives mgz equals 1/2 mv square plus 1/2 I omega square, where I equals 1/2 m big R square. But omega equals v over small r. Solving for v gives Formula 1. We can equalize first derivative to this expression by z to 0 to find that maximum is around z equals 0.6 L. Intuitively, in the beginning the yo-yo has roughly constant acceleration downward, but as the string unwinds, more of the energy goes into the yo-yo's rotational motion. In fact, the translational speed of the yo-yo goes to 0 when the string completely unwinds, at which point it's just spinning in place. Therefore, during the latter part of its fall, the yo-yo has upward acceleration, so the answer is none of the above. Which is answer E. This remains true regardless of the details of the yo-yo, because it only depends on the fact that the radius, small r, starts equal to big R and then becomes very small, since the axle is thin. In particular, changing how small r depends on z, or the moment of inertia of the disk, won't change the answer, and this was the solution to problem number 25.